Thank you for the introduction. Yes, we'll take you to the journey we had from axial to radial braiding machine concept, which has been, had some bumps on the way. But first, I would like to introduce our company. My presentation will contain the introduction of our company, the overbraiding equipment and associated parts, which parts you can produce with overbraiding equipment. Several comparisons have been made before, but I still would like to highlight it. And then our journey from axial to radial braiding and how we see the future for these kinds of machines and architecture. Our company was founded in 1982 in Tilburg in the Netherlands, and one of the first companies to braid with carbon fiber. Tennis racket in the market was an important one, hockey sticks, etc. And since '94, we started with the overbraiding technology, where you can deploy your fiber in the additive manufacturing process directly onto the core. Later in production of the crash cone, which is of the Mercedes McLaren SLR, one of the parts we have produced in the past. This will come in a presentation as well. We had capacity shortage on the braiding equipment, and this is the main reason why we started creating our own braiding equipment at that time, also to keep the know-how in-house as a pioneer. Capacity shortage on the braiding equipment, and this is the main reason why we started creating our own braiding equipment at that time, also to keep the know-how in-house as a pioneer. So we've built several braiding machines. People are asking to do the same, but then at their location. This is what we have done with several companies, also institutes. The Dutch Aerospace Laboratory, National Composite Center has the best of the best currently, and several other customers. Of overbraided components, our first success was an overbraided crash cone, and the triaxial architecture proved to have a very high damage tolerance and a low crack propagation. This will result in a high energy absorption. In this case, it was used for the crash cone application of the Mercedes McLaren SLR. After that, the Lamborghini Aventador was the next overbraiding component. 3 parts, A-pillar, support bracket, and the rockers. All parts contain a high degree of unidirectional fiber, so triaxial braiding. Products we produced, that was for the BMW i8, very complex parts, door frame, the rockers. They made 2 rockers, 20,000 cars, that means 80,000 rockers. And we had a waste rate of about 1.5%. So that is really, really low, even for BMW standards. Okay, the comparison between the architectures. Well, my colleagues already explained the architecture. We have seen the horn gear with the central fiber where we can feed in the UD fiber. This is the video how the motion of a normal axial braiding machine is going. You can see the carriers are moving around the pipe where the UD fiber is inserted, leading to this architecture. So if we look at the braiding fiber, we have the red and the blue one. This will have 2 fibers per machine, and then there's 1 position of UD, hence the ratio 2:1. So if we look at the architecture braid again, as I explained before, ratio is 2:1, so 33% of the positions is UD fiber. And during braiding, we will get no interlocking but nesting. So if we can look here, if we add layers on top of each other, from experience we know that next layers will nest into each other, but there's no through the thickness reinforcement. And as I explained before, when we look at this location, we have 3 fibers, we have 2 fibers, so it's not equal thickness. So if we look at the COBRACOMP architecture, using the pictures made by NZ. We see there are no gaps between the UD. As Xavier mentioned, it's 6 fibers, interlocking. And of course, when you stack layers on top of each other, you will have the nesting effect as well. 4 UD sections per layer. This will lead from 5. If we look at 2 gears together, they will have 5 braiding carriers and 4 UD positions. The center position will be inserted with 2 fibers. Therefore, we write 4 UD positions. And of course, the invention has been made by George Kawasaki. Our journey. Well, our first machines, they were axial. We had axial braiding machines. So the step was very logic to continue with the design of the new braiding machine in an axial way. And also the patent of George was represented in the axial design. But in the patent, the architecture is patented. So it does not matter if you do it by hand or with a machine, it's the construction which is protected. Our wish was not to use special gear modulus or transition gear ratios to design the machine. That was our basic starting point. And our first design we made, this is a representative first design. It had some speed errors. So if we look at the outer gear and the inner gear, they have to have the same rotation speed. And if they don't have the same rotation speed, we will get a speed error. Resulting is in the gaps, they are not aligning. You can correct that with extra gear sets or special modulus gears, but that was not the route we wanted to pursue. To make a comparison of possible solutions, my colleague made a very nice Excel tool where we could choose the number of notches per horn gear on the outside, the inside, the modulus, which is been fixed by commercial available module gears, and also the pitch circle of the outer and the inner gears. And it would choose, select a couple of matches, number of the tooth, the pitch diameter, etc. So there were some combinations possible. And the next output of this Excel document was to create a video of the machine. We had to fill the machine by hand. So indicate I want to have this position filled with carriers. And by doing that, we were able to do simulations with the amount of notches on the outer ring, notches on the inner ring. And there were several things which were important, which we found out. So in the evaluation we have made in the Excel document and CAD models, we checked the number of gears and notches. There were different ratios possible. The needed length compensation. So if we look at length compensation, the carrier has to travel from the inside all the way to the outside, and when it comes back in, the fiber should have tension. So this is determined length compensation. The larger the gears, the more length compensation you need. The larger the gears, the larger the carriers can be. So there's always a trade-off. So the maximum diameter of the carrier, it's important to have sufficient spool volume and amount of fiber for production. Another topic was the gap in between the gears. When there's a specific configuration, there's a gap which can exist, and that was not desired. So we had a threshold for the size of the gap. The carrier to gear ratio, well, that was also depending on the number of notches. We wanted to have a high UD ratio of 80% of positions. And we used different sets of commercial available gear modules. Well, this resulted in this table where we tried all kinds of configurations and checked the feasibility. But everything which is orange was not really a good match. So I don't see only the top line. It's a blue line. So that is a possible machine candidate. But the machine was too small to use for the propeller blade. So this was not a good viable option. So after spending quite some time looking at the actual concept, we had to draw our conclusions. The concept was also not scalable. There was only one blue line in the last table. There were difficulties due to the different horn gear sizes, length compensations, etc. So the solution was to look into the radial braiding machine concept. So for that, we made an evaluation. We have no experience with radial braiding machine design. So we started with the evaluation of which shape should the horn gears have for a smooth transition of the carriers. And from this evaluation, it turned out to be that the machine had to be completely spherical. So this is the machine design at the end, how it turned out to be. Machinability was very complex. We need 3D machining. But we managed to do that. The machine is finished, and we would like to show you that in the following video. Well, this video has been based on our CAD model, and the video has been organized by Euramaterials. Based on that, we had to start the feasibility study. So we machined the parts, and we have made a concept model, which has been exhibited at the JEC and the ITMA in Milan. So instead of using carriers, we have used flashlights to attract more visitors. But you can see the motion, it's really working. So the braided specifications, the sizes are 3.10 meter on the outside, 2.5 meter on the inside, 180 carriers. So if we have a section of 2 horn gears, there will be 5 braiding carriers available. 36 rows times 2 will make 3 times 36 position for the UD. And we will make the whole machine in segments of 6 parts. Below you can see the robot for manipulation, and we will look to have and add another robot for to hold the core on 2 ends. So in the near future, we will finalize the full machine, and the proposed end date is September. integration of the 1 or 2 robots. Then we will perform braiding trials for Colin Aerospace for the propeller blade. And we have 2 waiting customers for automotive to make some parts for trial, and also for the further material characterization. If you're interested, you can drop us an email, or also watch the COBRACOMP website for the latest information.